we sink our teeth into the main topic of this video, I need to bring you up to speed on some matrix arithmetic. Really, just two basic points. The first point is that we can multiply a matrix by a number, and when we do, the multiplication occurs in an element-wise fashion. For example, in order to multiply the number k by the matrix whose elements are A, B, C, and D, as shown here, we just take k and apply it individually to the elements of the matrix like this: k times A, k times B, and so on. Recall that in discussions of matrix vector multiplication, we went to great lengths to write the matrix to the left of the vector. We don't have the same worry when multiplying a matrix and a number, and we're okay writing the operation in reverse order like this. The second point I want to make is that we can add two matrices provided they have the same shape, that is, the same numbers of rows and columns. And when two matrices have the same shape, we add them simply by summing their corresponding entries. As an example, consider the task of adding the matrix ABCD to the matrix EFGH. Since these matrices have the same shape, we're good to go, and in this case, their sum is a matrix whose entries are A plus E, B plus F, and so on. I want to point out that by combining points 1 and 2 seen here, you can also figure out how to subtract one matrix from another. The operation is mathematically obvious, as they say, and you can probably tell it will amount to subtracting corresponding elements belonging to matrices of the same shape. Now, I have one more related point to make. Although the point is not about basic arithmetic, it is still important background. You know, of course, that taking the product of the number 1 and any other number x simply returns x. In the world of matrix vector multiplication, we can easily find an analog to multiplication by 1. Consider, for example, applying the matrix 1, 0, 0, 1 to the vector x as shown here. After carrying out this matrix vector multiplication, we find our result has left x unchanged. Since multiplication by this matrix leaves a vector identical to what it was to begin with, we'll often write it simply as capital I. In general, I is a square matrix. It has the same number of rows as it does columns, with 1s along its diagonal and 0s everywhere else. I'll add that we often refer to capital I as the identity matrix. We're now in a position to begin the broader discussion we're really interested in having. That broader discussion revolves around solutions to problems like this. Suppose I give you a square matrix A, something like 2, 1, 1, negative 1. Then, suppose I challenge you to find a number lambda and a non-zero vector v such that A times v gives the same result as the one we would have obtained had we just multiplied v by the number lambda. Now, I want to stress that this unknown vector v is not just made up of all zeros. Yes, a vector v made up entirely of zeros paired with any number lambda would satisfy the equation given. But such a solution would amount to a statement that isn't really that mathematically interesting. Something like 0 is equal to 0. It's for that reason that we stipulate v must have at least one non-zero entry. Okay, ground rules for finding a solution are in place, so let's tackle the problem. We'll start by finding lambda. Okay, we need to solve a times v is equal to lambda times v. Moving lambda v to the left side, we see that this is the same as saying a times v minus lambda times v is equal to 0, or rather, the vector made up entirely of zeros. I might then factor out the vector v on the right to get a statement like this. There's a problem here, though. We know how to subtract one matrix from another, but we don't know what it means to subtract a number like lambda from a matrix. So it seems that we need to modify our approach a bit. This is where knowing about the identity matrix comes in super handy. We'll go back to this line here, and we'll replace V with the identity matrix times V to obtain this. The genius of this move is that it allows us to factor out the V vector like this, leaving behind something between the brackets that now makes sense to us. To see that better, let me write the statement out in full. You can see that lambda times I is a matrix, and it has the same shape as the matrix A. So we know how to deal with what's going on inside the brackets. That leaves us with this straightforward statement involving a matrix vector multiplication. Now, pause and reflect on what we've ended up with here. We're saying that if we manage to solve our original problem, then we will have found a matrix that maps a non-zero vector V to the origin, represented here by the zero vector. Our previous experience tells us, therefore, that the determinant of this matrix must be 0. That's an important observation because that's the key to nailing down lambda. We recognize that a lambda that makes up part of our solution must be a number that also makes this statement about the determinant of this new matrix true. Applying our formula for the determinant of a matrix with 2 rows and 2 columns, we turn this statement into one that is much more familiar. We now see that the numbers lambda we're looking for are nothing more than the roots of a quadratic function. And in this case, those roots are 1 plus the square root of 13, all divided by 2, and 1 minus the square root of 13, again, all divided by 2. These roots, I'll call them lambda 1 and lambda 2 respectively, are known as the eigenvalues of the matrix A, that is, the matrix we were originally given. Catch your breath here for a second because we're not done. We still need to find our non-zero vector V, and since we have 2 eigenvalues, we have to consider the possibility of finding one V for each. To find our vector, or vectors, we need to go back to an earlier point in our calculations. We'll go back to this point, and specifically to this step here. Now, what we'll do is sub in our known values for lambda and solve for the still unknown entries of the vector V. Let's start with lambda is equal to lambda 1. The statement we see here is nothing more than a system of 2 linear equations with 2 unknowns, V1 and V2. From the first of these equations, we find that V2 is equal to negative 2 minus lambda 1, all in brackets, times V1. If we sub that into the second equation, we get this. And that simplifies to this. Because lambda 1 is a root of the quadratic function lambda squared minus lambda minus 3, we know that this stuff contained in the brackets must be equal to 0. That means that no matter what value of V1 we choose, this modified version of equation 2 will be satisfied. Since we want to avoid the situation where V is made up entirely of zeros, we choose a value for its first entry that's something other than 0. So let's choose V1 is equal to 1. If that's the case, then this tells us that V2 must be this. So V is this vector here. Given that lambda 1 is equal to 1 plus the square root of 13, all divided by 2, we can say specifically that V is this vector here. We call this vector the eigenvector associated with the eigenvalue lambda 1. Together, this eigenvalue-eigenvector pair is a solution to AV equals lambda V for the matrix A we were originally given. Notice that almost exactly the same set of steps leads us to conclude that this vector is the eigenvector associated with the eigenvalue we called lambda 2. This pair is yet another solution to the puzzle we started with. Speaking of solutions to the puzzle, it's important to emphasize at this point that the eigenvector portion of a solution to our problem won't be unique, even for a fixed eigenvalue lambda. This is a consequence of the fact that we got to choose one of the entries of the eigenvector. Depending on the choice we make, our eigenvector will be different. However, in this case, even if you make one choice and I make a different choice, the eigenvectors we find would be collinear. We've covered a lot of ground, so now's a good time for a recap. In this video, we covered some basics about arithmetic with matrices, but that was really to support our ability to do something more important. That more important something amounted to finding the eigenvalues of a square matrix and their corresponding eigenvectors. At this point, you should be able to explain what an eigenvalue-eigenvector pair is, and you should be able to identify these for certain kinds of matrices. You're not able to handle all possible square matrices yet, not even all square matrices that are reasonably small in size. But you'll hone your ability as this week goes on. Basically, I'm saying there's more to come. Don't forget that watching this video is pointless if you don't back it up with action. Read the notes provided and try the exercises. If you have questions, hit the forums. Better yet, hit the forums if you want to answer questions posed by your classmates. Studying for math is way more fun and possibly way more effective when you do it by building community.